Okay, now we can talk about blocks in a blockchain. So we so far covered cryptographic algorithms that we mostly use in blockchains. Those are cryptographic hash functions and digital signatures. So let's recap cryptographic hash functions in blockchains. Within a blockchain network, cryptographic hash functions are used for many tasks such as address derivation, creating unique identifiers, securing the block data. Here, a publishing node will hash the block data, creating a digest that will be stored within the block header. So there are different ways of doing it. Maybe you can simply hash the whole block data, but in Bitcoin or cryptocurrencies, we want to search in a very fast way to find the transaction. So instead of hashing the whole block, we actually take the hash of every transaction, then take the hash of pairs of transactions to create a Merkle tree, and then at the top we had obtained a Merkle tree hash value and put that in the header. We also use hash functions to secure the block header. A publishing node will hash the block header and it will be included in the next block header. But here the important thing is that this is actually where the mining happens in cryptocurrencies. Generally, aim is to obtain a hash value that is smaller than the difficulty parameter. Okay. So once you obtain such a hash output, you include it in the next block. So this way you provide the security of the block header. Okay. So let's talk about blocks. Each block in a blockchain can contain 0 or more transactions. So this is important. A block in a blockchain actually might not contain any transactions at all, but you might still add that block. So we will mention it briefly in the cryptocurrencies. For some blockchain implementations, a constant supply of new blocks, even with 0 transactions, is critical to maintain the security of the blockchain network. By having a constant supply of new blocks being published, it prevents malicious users from ever catching up and manufacturing a longer altered blockchain. Okay, so this is important. Just go back to our Lego analogy. So we are adding new blocks. Think about it, creating a Lego tower. So you put each Lego piece at the top. So assume that, for instance, at Bitcoin or any cryptocurrency, assume that people stop sending money to each other. So if you stop creating new blocks at that point, your tower stays at the same height. So an attacker might go back and create new blocks and create a new tower with new blocks, and new tower might be longer than your previous tower. So for this reason, in cryptocurrencies, you have to constantly add new blocks, even if there is no transactions at all. So for the Bitcoin, this adding a new block actually determined as that to happen in 10 minutes. So in Bitcoin, if nobody makes any transactions at all in 10 minutes, still the miners create a block. But that block does not contain 0 transactions, but it contains a single transaction where they actually reward themselves as the founder of the block. So that transaction is called Coinbase. But idea is that we have to constantly supply new blocks. If this does not happen, and in some cryptocurrencies this happened because people lost interest in that blockchain or in that cryptocurrency, so miners stop mining. So the blockchain actually stops at some point, and that cryptocurrency actually becomes useless and nobody uses it anymore. So hundreds of cryptocurrencies actually are lost in this way. Okay. Yeah, maybe, because there are thousands of cryptocurrencies since the Bitcoin, and there's actually a web page that lists cryptocurrencies that are no longer used. So yes, 700 sounds like a correct number. So it must be more than that. Okay, the data which comprises a transaction can be different for every blockchain implementation. However, the mechanisms for transacting is largely the same. A user sends information to the blockchain network. So this means that if you want to make a transaction, your software, like your wallet, creates that transaction. and announces it to the network. Okay, and generally you don't announce it to the whole network. Maybe you actually are connected to like 6 people on the network. You simply announce your transaction to the 6 full nodes, and that 6 nodes will send this transaction to other nodes that they are connected to. So this way your transaction actually sent to whole network. The information sent may include the sender's address, sender's public key, a digital signature, transaction inputs and transaction outputs. And actually this is valid for also cryptocurrencies. While primarily used to transfer digital assets, transactions can be more generally used to transfer data. So this is important. So in cryptocurrencies, we are always focusing on transferring digital assets, but you can also, create more general blockchains where you actually use it for transferring data. In a simple case, someone may simply want to permanently and publicly post data on the blockchain. This actually happens in Bitcoin because after the opcode ob return, actually since it returns true, the rest of the code is not run by the nodes. So you can actually put any data there, and some people announce things like, Alice, will you marry me, or that kind of announcements. So you can actually go to Bitcoin blockchain. Actually, we will do it next week and see what kind of hidden messages people put inside the blockchain. So you can write it there and it stays there, so you can actually announce something permanently. Like in the Genesis block of Bitcoin, the Satoshi put the headline of New York Times. So that kind of practice people still keeping, and some people, announce that they are married, and that's so on. And some people, Bitcoin users, doesn't like this approach because you're kind of, wasting the blockchain because you are storing data that is not that necessary for Bitcoin to work. So some people does not like that opcode where people, put messages afterwards. But still you can do it. But you can also create different blockchains where you can actually, publicly announce some data. For instance, like for a university, you can publicly announce all of the diplomas you create, but of course not providing the full name of the person who received the degree, so that anybody can check if a degree is valid or not by looking at your blockchain and so on. In the case of smart contract systems, transactions can be used to send data, process that data, and store some results on the blockchain. NFTs are some examples to this. For example, a transaction can be used to change an attribute of a digitized asset, such as the location of a shipment within a blockchain technology-based supply chain system. So if you create a blockchain for a supply chain system, you can create smart contracts, which actually modifies the location of a shipment and so on. We also talk about asymmetric key cryptography, mostly focusing on digital signatures. So asymmetric key cryptography provides the ability to verify that the user transferring value to another user is in possession of the private key capable of signing the transaction. So this is actually what we do in digital signatures. So every user creates private and public keys. Private keys are used to digitally sign transactions. Public keys are used to derive addresses. Also, public keys are used to verify signatures generated with private keys. So actually nodes just check your signature by doing this. So this is what we talk about when we talk about elliptic curve digital signature algorithm and Schnorr signatures. So let's look at permission blockchains. Some permission blockchain networks can leverage a business existing public key infrastructure for asymmetric key cryptography to provide user credentials, rather than having each blockchain network user manage their own asymmetric key. So this is a good approach actually. So in Bitcoin or similar cryptocurrencies, you just use a software, a wallet software, and you create your own public and private keys. But in your company, for instance, if you already have a public key infrastructure, if everybody has already a public key, then you can continue using that infrastructure. So you don't need to, create new public keys or private keys for the users. This is done by utilizing existing directory services and using that information within the blockchain network. Blockchain networks which utilize an existing directory service can access it via existing protocols, such as the Lightweight Directory Access Protocol, LDAP, and utilize the information from the directory natively or import it into an internal certificate authority within the blockchain network. So you don't have to use a Bitcoin-like wallet software. So now it is a good time to talk about digital wallets. But first, let's talk about physical wallets. So a wallet in your pocket actually generally have three main purposes. It stores your cash, right? So whenever you want to buy something, you just remove cash from it. And if somebody gives you some cash, you put it back. So it looks like a physical wallet has three main purposes: storing cash, paying cash, and receiving cash. So when you look at the internet and ask what a digital wallet is, many books, web pages, blogs claim that digital wallets are digital analog of physical wallets, and they are used to store your cryptocurrency, send cryptocurrency, and receive cryptocurrency. But the main problem here is that digital wallets do not store your cryptocurrency, okay? This is very, very important. Your cryptocurrency is not in your wallet. And since it is not in your wallet, you don't send or receive anything, okay? So this is very, very important. And you might think that, okay, in theory, it is like a physical wallet, but actually it is not, because once you say that it stores cryptocurrency, people have starting misconceptions. For instance, years ago, I talked to a forensics investigator, and they said that a convict admitted that he have a wallet software in his laptop, and there are some Bitcoins in it. So I asked them if they transferred it to a secure wallet address so that nobody withdraws it. And the forensic investigator kind of got surprised and said that, okay, it is in the laptop, in the wallet, and the laptop is turned off. How can they, withdraw the money? Or how can transfer the Bitcoins to someplace else? And I tried to explain that the Bitcoins are not in the laptop or in the wallet software or anything. It is on the blockchain. And if a friend of this convict also knows the private key, they can simply transfer it to someplace else. So it took some time to convince them, but at the end, I just asked the wallet address, and from the internet, I looked at the transactions and showed them how much Bitcoin in that wallet address is, and then they realized that it is not actually in the software, but it is on the blockchain. Okay, so this is really, really important. Some people still think that it is in the wallet. So wallet does not store your cryptocurrency. So then the question is, what does it store? So it actually stores your private keys and public keys generated from there, and sometimes more. So with some blockchain networks, users must manage and securely store their own private keys, because only you know the private keys, so you have to store it by yourself most of the time. So for this reason, you use software called wallets to securely store them. So this software is often referred to as a wallet. The wallet can store private public keys and associated addresses. It may also perform other functions, such as calculating the total number of digital access a user may have. So this is actually what I was trying to tell you. So maybe you have 10 private keys and maybe 10 public keys from those private keys. So you have actually 10 addresses, and maybe all of them has received some amount of Bitcoin. So your wallet software actually search the blockchain for all of the transactions associated to these addresses, and the wallet gives you the total running total, saying that you have this amount of Bitcoin. But in practice, you don't have it as a single amount. You actually have it distributed in many different transactions. Whenever you want to spend them, your wallet software actually does it for you. So if a user loses a private key, then any digital asset associated with that key is lost because it is computationally infeasible to regenerate the same private key. Recall that we have to solve the discrete logarithm problem to capture that private key, which is currently infeasible. And if you somehow build a very big quantum computer, then you can do it. But currently, we don't have that technology. So now it's a good time to talk about ledgers. So we said that we distributed these ledgers to everybody. So it is transparent and we distribute it. But what is the point of doing it, or what are the advantages or disadvantages compared to centralized ledgers or centralized ownership? So think about the bank. All of the ledger is kept by the bank itself. So if somebody keeps it and doesn't share it with other people, if they don't distribute it, what can go wrong? So let's look at the pros and cons. So let's look at the cons of centrally owned ledgers. So centrally owned ledgers may be lost or destroyed. So once it is lost, you cannot regenerate it, right? So you have to keep backups and so on to manage this. But second thing is that centrally owned ledgers may be on a homogeneous network. So here what we are trying to say is that, for instance, in a bank or in a different company where you keep a centralized ledger, maybe all of the computers are identical. All of them are running the same operating system, same software, same versions, and so on. So it is homogeneous. But this may create a single point of failure, since all of them are the same. But think about Bitcoin or any cryptocurrency or any this kind of blockchains. People are running different devices like laptops, desktops, mobile phones, tablets, and they're all running on different CPUs, RAMs, and so on. They all have different software, different operating systems, but the network still works. So it is sometimes good to have an heterogeneous network to avoid single point of failure. Moreover, centrally owned ledgers may be located in a specific location. So this is a very bad idea for natural disasters. So most people, most of the time, keep a mirror of their databases in a different building. But even if you store two copies in two buildings next to each other, a natural disaster might destroy both of them. I think which happened in Katrina natural disaster in the United States. So some of the companies have to, become bankrupt because they lost all of their data. So keeping them in a specific location is not a good idea. The transactions on a centrally owned ledger are not made transparently and may not be valid because we don't know what happens because it is not transparent. So you know that you received some money from your friend because your bank says that you received such a thing. But what if they don't tell you, even if you received it, right? You have to trust your bank. The transaction list on a centrally owned ledger may not be complete. This is what I was trying to tell. Maybe you received some money. Actually, I sent some money to all of you, but if you haven't heard from your bank, maybe it is your bank fault. Think about it in this way. Maybe I really sent some amount of money before the start of this lecture, but your bank do not tell you because you don't have the full list, right? You cannot know if you received and they didn't tell you. Of course, I'm joking, but you have to trust the system at some point. The transaction data on a centrally owned ledger may have been altered. Again, we have to trust the company, also the workers. The centrally owned systems may be insecure because a user must trust that the associated computer systems and networks are receiving critical security patches and have implemented best practices for security. In the past, many incidences happened. On the newspapers, you hear stories about it. For instance, a bank worker may go home, but keep his computer turned on in the weekend so that he can connect it from home and work from home. And this kind of connections allowed hackers to stole some money from the bank and so on. Moreover, the system may be breached and have had personal information stolen because of insecurities. So this is why distributed ownership of ledgers has some pros compared to centralized ownership. Okay. So how do we actually use the blockchain? Blockchain network users submit candidate transactions to the blockchain network via software. So in case of cryptocurrencies, using your wallet software, you actually create a transaction and announce it to the network. But at this point, it is not actually written to the block. Okay, it is currently just announced. In the Bitcoin, it is kept in the mempool. And if a miner includes it in a block, then it becomes valid. For many blockchain implementations, once a pending transaction has been distributed to nodes, it must then wait in a queue until it is added to the blockchain by a publishing node. Transactions are added to the blockchain when a publishing node publishes a block. The block header contains metadata for this block. The block data contains a list of validated and authentic transactions which have been submitted to the blockchain network. So this is the main idea of the blockchain actually. Validity and authenticity is ensured by checking that the transaction is correctly formatted and that the providers of digital assets in each transaction listed in transaction input values have each cryptographically signed the transaction. So this is actually what full nodes does. They check if your transaction is valid by checking all of the signatures and so on. This verifies that the providers of digital assets for a transaction had access to the private key which could sign over the available digital assets. The other full nodes will check the validity and authenticity of all transactions in a published block and will not accept a block if it contains invalid transactions. So this is the whole idea. This is why when you create a transaction, you also pay a fee in Bitcoin or in similar cryptocurrencies, because you're actually forcing full nodes to perform operations, because you announce a transaction and now they try to validate it. So actually they are spending some electricity, some computational power sometimes. So you have to pay some fee so that, you know, this way they are encouraged to, you know, include it in their block. So miners, the main idea for miners to include your block, your transaction in a block, is that they will receive some fees at the end. So let's look at the structure of blocks. Generally, we divide blocks as block header and the block data. So for the block header, we have things like the block number. In cryptocurrencies, this is also known as block height. It also contains the previous block header's hash value. Also, it contains the hash representation of that block. Again, there are different methods like generating a Merkle tree and storing the root hash, or by utilizing a hash of all the combined block data can be used. It also contains a timestamp, generally in the Unix format, the size of the block, the nonce value if it is a permissionless blockchain, and you know, if the miners are using proof of work consensus model, this nonce value is used for mining. In the Bitcoin, this is 32-bit value. So they actually try all of these 32-bit value, which can have 2 to the 32 different values. So, but trying, you know, performing 2 to the 32 hash operations takes less than a second. So this nonce is tried in a very fast way. So for blockchain networks which utilize mining, this is a number which is manipulated by the publishing node to solve the hash puzzle. So once you try all of these values, which takes less than a second, since if you didn't receive the hash output, which is less than the difficulty value, this means that you have to modify your block so that it will change your Merkle tree, so it will change your block header. Now you will try to take the hash of this block header, so this nonce value will be tried again and again. If you look at the block data, simply it's actually contains a list of transactions and ledger events included within the block, and depending on the blockchain, it might contain some other data. So here is a picture So this is how it works. Let's think about Bitcoin. So you have all of the transactions listed here, but by taking the hash of them in a Merkle tree way, at the top you have your Merkle tree hash. So you take it here and put it here. This is your hash value of the block. And you choose your nodes, for instance, 0. You put your current time and put the previous hash of the previous block header. Calculate the hash of it. If it is less than a value, this means that you solved the cryptographic puzzle. And now this block becomes valid. And the hash output is put here for the following block. If it is larger than the target, then you have to change the nonce. You try all of the nonces and it is still higher than the target, then you have to modify this block data. Since you have a coin-based transaction here, you generally modify it, and this way this part becomes different. So you take the hash of it again to see if it is smaller than the target. So this is actually how mining works on a permissionless blockchain. But if it is a permissioned blockchain, you don't have to, solve a cryptographic puzzle. Maybe you have the authority to create a block. So you simply create this block, and you don't care if the hash of this is smaller than some value or not. Okay.